Hello, everybody. This is Mariana Ruys from Fluitec Team Europe. Um, I'm very happy to introduce to you Douglas Purnell, um, our senior research chemist at Fluitec, and he will be giving us knowledge on Know the Enemy Varnish. So here you go. And oh yes, after the session there will be 5 minutes or so left, time left for Q&As. Enjoy.
Greetings, everyone. My name is Douglas Purnell, and thank you for taking the time to listen to my discussion titled Know Thy Enemy. If you're a history buff, or if you're even familiar with the 48 Laws of Power, you might be familiar with Sun Tzu's famous quote: Know thy enemy and know yourself. In 100 battles, you will never be defeated. When you are ignorant of the enemy, but know yourself, your chances of winning or losing are equal. If ignorant both of enemy and of yourself, you are sure to be defeated in every battle. But how does this pertain to varnish? And what's the purpose of knowing said enemy? Oxidation of lubricants results in the formation of chemical byproducts that may result in varnish. Varnish has been defined as an insoluble film composed of primarily organic residues that coats the internal components of machine lubrication systems. There are many reasons why understanding more about varnish, or as Greg Livingstone calls it, the cholesterol for lubricants, behaves and even forms. The first reason is to determine if more antioxidant in oil is good for the lubricant. Next is, does the carrier fluid play a role in determining the lifetime of oil? And finally, what are the byproducts of a culmination of different additive chemistry? A common strategy to extend the life of industrial lubricants is to formulate lubricants with antioxidant packages to reduce varnish formation. Additives can be purchased from many companies. To name a few, these include Lubrizol, Apton, Infinium, and King Industries. In this slide, I would like to actually show the action mechanism where a chemical species initially loses its proton and then goes into a system where it's introduced to oxygen, then is then going through a chain termination and chain breaking system, which then leads to a termination, whether it be through a peroxide decomposer or a UV absorber. So why do we want to qualify the individual antioxidants? This is because they work in something called synergism and will let us understand in a great detail how the lubricant is degrading. In this example here, we're showing a free radical interacting with a system which is composed of an aminic and phenolic antioxidant package. First thing we witness is that the free radical accepts an electron from the electron donating aminic free radical, converting the antioxidant into a stable radical. In turn, the amine then reacts with the phenol, where the phenol donates an electron to then convert the antioxidant into a stable radical. Our journey to understanding how lubricants act under different conditions begins with knowing where we started. We have selected two fully formulated lubricants labeled Product 1 and Product 2, a solubility enhancer, a Group 2 base oil, and a phenolic and aminic antioxidant labeled Additive 1 and Additive 2 respectively. Our methods rely on four different aspects of our study. The first one being is to model formulations using a exaggerated concentration of antioxidants to better monitor, observe, and model reactions and identify possible side effects of commercial antioxidant packages. The second being to see the effect of individual formulation components and their mixtures. Third being aging the lubricants using TOPP methodologies to see the course and the progression of degradation. And the last one is to use oil analysis and physical observations of deposits and reactors. This will all be accomplished, or was accomplished, by utilizing 5 different ASTM methods. These including D445, D7843, D6971, D7414, and finally D7873. From basic arithmetic, we have been taught that 1 plus 1 equals 2. and the total is equivalent to the sum of its parts. In the ruler graph shown, we would like to illustrate how this is not particularly true in this case. The black line represents 4% additive 2, or the phenolic antioxidant in group 2 base oil. The brown line corresponds to the aminic antioxidant, or additive 1, in group 2 base oil at 4% as well. The red line is the mixture of the aminic and phenolic antioxidants mixed at the same time at 4% of each additive. However, this is when our first curveball is thrown in. When observing the data, we've noticed that the additives in solution only with group 2 base oil have zero contribution in regions where they do not have functionality, meaning the aminic antioxidant does not have a phenolic functionality, and the phenolic additive does not have aminic functionality. However, when they are mixed, we are witnessing a stronger signal in the aminic region. But why? To understand this simple system, we will now display FTIR data to illustrate the empirical contributions. It should be noted that for this ruler analysis, all samples were diluted to a 9:1 ratio in a group 2 base oil, as the 100% mixtures oversaturated the system, and we were not successfully allowed to quantify the amount of additives inside. We are now completing the same experiment from ruler analysis in the previous slide. Here the black line represents the group 2 base oil by itself, while the blue and the red represents additive 1 and additive 2 at 4% in base oil. Antioxidant additives were selected at high concentrations to see distinct peaks from each other in the base oil. In turn, they allowed for more straightforward interpretation of the data. From this analysis, we recorded that there are no unusual peaks within the group 2 base oil, and the contribution peaks for additive 1 and additive 2 can be seen on the left. So using our basic arithmetic, we would expect no additional peaks, but we know that was not true when looking at ruler. So will we see the same interaction or anything different as we've seen before? Everything appears to check out. Our arithmetic is correct, and there's nothing out of the ordinary apparent. But let's zoom in and observe the spectra with a little more scrutiny. We have found that a peak appears at 3380. This is where we begin to scratch our heads, because an apparent reaction is occurring in the same region where we're witnessing NH stretching for secondary aromatic amines. So the question now is, are we creating a new chemical moiety? Are we seeing hydrogen bonding? Or have we activated a resonance structure? So now that we've opened Pandora's box by observing the 4% additive contributions, we now have to ask ourselves, will we see the same information and the same peaks observed when observing the 2% of each additive added in group 2 base oil? Inclusive, and allow us to confidently state that the peaks containing 2% additive 1 and additive 2 are roughly 50% of what is observed in the mixture with 4% additives 1 and 2 as well. In addition, the peak observed at 3380, it is present in the 2% mixture. However, it's not at the 50% of the peak that is observed at the 4% mixture. Now we have all the groundwork out of the way, we can speak about the experiment. Let's observe the tubes in the bath. The images show the testing apparatus under 180 degrees centigrade for 5 days. From these images, one can notice a distinct color change in the bottom right 2 tubes, while the others remain clear. This only occurs when both aminic and phenolic additives are present, resulting in a color change in the gas phase. As time continues, deposits eventually form above the oil line. These observations indicate possible chemical interactions in the gas phase between additives and are likely to occur in the liquid phase as well. Recall a few slides back where we witnessed an additional peak when comparing 2% and 4% additive mixtures in group 2 base oil. Gas phase observations were also noticed at 120 degrees centigrade as well. However, the coloration is different than that observed at 180. Perhaps it's different reaction chemistry. But similarly, deposits are also formed above the oil line as in 180 degrees centigrade, but only when the two antioxidants additives were present. On this slide, we'd like to take the opportunity to observe the empty testing vessels. With the realization of this phenomenon, I guess we can thank Steve Jobs for the invention of the iPhone, as we captured the evolution of the age sample at such high resolution. It's safe to say more antioxidants does not result in fewer deposits. Also, it's now an excellent time to point out the crystal formation on the mushroom condenser. Please observe that there are more crystals on the 2% additive mixture mushroom condenser than that observed on the 4% additive mixture. However, there's an inverse correlation when comparing the glassware, where the 4% additive concentrations seem to have a higher concentration of crystals formed on the glass itself when comparing to 2%, where there may be lower amounts of crystals formed on the glass, but higher amounts of crystal formations on the mushroom condenser. While investigating these samples, comparing the virgin samples of the product and mixtures to aged samples is appropriate. Now, I know there are a lot of values present on this slide, but bear with me. Looking at the data for group 2 base oil, one would think that the 180 C at a 5-day aging process would have a higher MPC in addition to an increased varnish mass, especially by knowing that for every 10 degrees Celsius increased, the rate of reaction doubles. And with 180 centigrade testing conditions being 60 degrees higher than that for those tested at 120, the reaction would take place 192 times quicker, and there would be more byproducts. However, we see that for this particular example, the MPC of group 2 base oils at 180 degrees for 5 days does not show elevated levels compared to 6 weeks in virgin samples. However, the varnish weight is only 0.3 milligrams compared to the 1.9 recorded for the virgin carrier fluid and 1.3 milligrams for the same carrier fluid. For the remainder of the additive containing products, there is no correlation between varnish weights and MPC values. Group 2 oil exhibited a lower MPC value and resulted in fewer observed deposits than samples with antioxidant additives. So let us ask ourselves, does the glassware tell the same story? So now that we know that more doesn't equal better, we'll now like to do a comparison between the group 2 base oil compared to group 2 base oil with 2% additive 1 and 2% additive 2, and also the group 2 base oil with 4% additive 1 and 4% additive 2. So when looking at A, which are the first two images, we see that the group 2 base oil, after 5 days at an excruciating and grueling 180 degrees centigrade being aged, you see that the base oil is pretty much is holding up. With the varnish potential being 6.7, yes, there are some visual deposits forming on the glass, but if you move your attention over to the next set of images in point B, you see that the 2% of additive 1 and 2% additive 2 within that same group 2 base oil, that the delta E is 56.9. Right? So from our contributions from ruler analysis as well as FTIR, you would expect that the trend of adding double the concentration, pretty much bringing it from 2 to 4% of additives 1 and 2 respectively, we would expect to see a higher varnish on the glass in addition to there being a higher delta E. However, we are not seeing that. While there are similar traits between B and C, such as us still seeing the formation of varnish above the oil line, that trend does not really cross over to the delta E or the MPC patch, where the delta E value is held at 58.8. And if you're familiar with the MPC method, you know that these values are within the error limits of the method. And allows us to say, okay, even though there are higher MPCs observed at multiple treatments, it doesn't necessarily mean that this will equate to more visual deposits. And allows us to kind of steer our investigation with looking through a new lens and asking ourselves the question, is the group 2 oil showing oxygen absorption earlier without any antioxidants present? But before we go through this, we're going to observe the FTIR of the group 2 base oil with 4% of additive 1 and additive 2 during the aging process. This will help us figure out the progression and see what exactly is happening at the chemical level. When comparing the age aliquots utilized during FTIR analysis, we are seeing the expected trend of phenol and amine peaks decreasing as time elapsed increases, as shown in the image here. From this close-up, we are able to clearly see the reduction in magnitude of peaks, but this is not the only thing we are seeing. So from looking at this image, the first observation we should take into plan is the actual 1700 peak. This peak is associated with conjugated acids and is only observed in the 1, 3, and 6 week TOPP samples at 120 degrees Celsius. Interesting enough, after 3 weeks, you start to witness the carbonyl peak at the 1710 region. While these peaks for 1710 are only present in the 3 and 6 week samples, they are only a fraction of what is seen in the 180 TOP testing, which is the pink line. Now, with us seeing this, will be the appropriate time to answer the question in the previous slide, where we asked the question if the group 2 base oil is showing oxygen absorption earlier without antioxidants present. In the current slide, we will look at the spectra with virgin group 2 base oil and its weekly age samples compared against 4% of additive 1 and additive 2 at 180 degrees. So the first thing we'd like to point out is that the top image, we would like to show the actual progression in the formation of the carbonyl peak at 1710. As you can see, it did not take long for the peak to arrive. After a week, we see a predominant peak at 1710. But how is this comparable to an additive mixture of both additives being at 4%? So here's where things get interesting. To save some time, I'm not going to walk through all the spectra, but in the bottom image, when comparing the degradation of group 2 base oil with the progression of the mixture described of 4% additive 1 and 4% additive 2, the base oil after a week at 120 has a larger quantity of carbonyl moieties present compared to what we are observing in the 180 degrees centigrade TOPP test of the 4% of each additive, which resulted in the highest level of carbonyl peaks at the 1710 region. So what does this actually tell us? The short answer is the additives are doing their jobs. At this point, we have answered many questions, but we have also created more questions that need to be answered. So moving forward, our course of action will be to do several things. The first is to use NMR techniques to characterize varnish fragments. Also, these same fragments will have FTIR analysis conducted on the methylene chloride rinses from the glass, coil, and mushroom condenser. And finally, we'll repeat these experiments with different base oils, because if you recall from the introduction, one of our questions was, is selecting a base oil something that needs to be considered? Because at this point, we're also seeing that this may be something we may need to look at when comparing choices for selecting a antioxidant. So in closing, from our study, we have realized that reactions taking place not only occur in the liquid phase, they also occur in the gas phase. Secondly, deposits are formed extensively when AO packages are present, indicating that MPC and deposit contributions come from the degradation of antioxidants not soluble in the oil. Next, we've learned that accelerated oxidation at 180 is opening a different reaction path than what is observed at 120, yielding fewer deposits but higher MPC values. And finally, the model formulations, accelerated testing, and high concentration treatments have allowed us to explore oxidation reaction pathways, pointing to further work for deposit and gas phase characterization. From all of this data and all of this research, it's easy to see that there are many things that need to be done, right? Not only do we need to expand our research, we also need to take time and answer questions and thank those who have watched this video. So if there are any questions, please feel free to email me at d.purnell@fluitec.com, and I'll be sure to answer your questions. So without further ado, I hope you all enjoyed this conversation, and I look forward to your questions. Hope all is well, and I'll talk to you soon. Enjoy the rest of the seminar. Bye.
Thank you so much, Douglas, for this interesting presentation. So we still have a couple of minutes left. So I would propose to those who are having questions to raise them right now. And if there are no questions, that means that you have done a great job, Douglas. And they probably come up via email. So, but let's wait another 30 seconds.
Okay. Yeah, this was a topic that was very, very vast, right? So it's a study that, as you see, took 6 weeks just to age the oil, right? Not even for characterization or anything else like that. And it's something that I really believe we need to, be on the forefront of, because we all know that varnish doesn't necessarily, have the same, the same characteristics. Not all varnish will be the same. Well, in theory, that's what I believe. And I honestly feel that by us looking at the reaction paths, we'll be able to not only be able to trend, how varnish is formed, but we'll be able to give insight to our customers to what conditions actually are conducive to them growing, and so on and so forth.
Okay. Thank you so much, Douglas. I'll end the stream right now. Thank you and have a nice day.
All right, same to you.
Thank you.
Bye.
Bye.